Welcome back to Physics 192. I'm Gerard Blanchard. Last time we introduced capacitors into our electrical circuits. And a capacitor is essentially a pair of parallel plates with a gap in between that has a positive charge on one plate and an equal negative charge on the other plate. And the fundamental property of a capacitor is that the voltage across the capacitor is proportional to the magnitude of the charge on the plates. And current brings charge to the capacitor. When a capacitor is charging, the current is bringing positive charge to the positive plate and negative charge to the negative plate. And when a capacitor is discharging, the current is bringing positive charge to the negative plate and negative charge to the positive plate. Let's look at a simulation of this so that you can understand that better. Here we have a circuit consisting of a capacitor, a couple of resistors, a battery over here, and a switch. So we'll assume that the capacitor is initially uncharged. So there's initially zero voltage across the capacitor. And I will close the switch, and what will happen then is that a current will flow from the battery down these wires and into the capacitor. So we will charge this plate of the capacitor positively and this plate of the capacitor negatively. We'll measure the current and the voltage at the location of this probe. That'll show up in these two graphs down here. So initially the voltage of the capacitor is zero because the capacitor is initially uncharged. But as we bring charge to the capacitor, the voltage across the capacitor will increase and the current to the capacitor will decrease. Let's go ahead and show that. Close the switch, and now you can see current flowing from the battery across the switch, across this resistor, and into the capacitor. You can see that it's bringing positive charge to this side, and it's taking charge away from this side, leaving a negative charge on the negative plate. The voltage across the capacitor was initially zero, and over time, as we brought positive charge to the positive plate and negative charge to the negative plate, the voltage increased. And you can see that it is exponentially approaching 1.5 volts, the voltage of the battery. The current, on the other hand, started off at its highest value, and the current decreased as time went on. And the reason for that is, if we consider Kirchhoff's voltage law, let's start at this point that I've marked 0 volts. As we go across the battery, we go up in potential, or up in voltage. And then as we go across this resistor, the voltage drop across this resistor is equal to the resistance times the current. Then we go across this capacitor, and we're going from the positive plate to the negative plate, so we're dropping in voltage. So actually, if we were to start here, we would go down by a certain voltage and then up by a certain voltage across the battery. So the voltage difference across the resistor decreases as the capacitor becomes more charged, or as the voltage drop across the capacitor increases. The voltage from here to here, from the bottom to the top, is always going to be 1.5 volts. That voltage drop has to be shared by the resistor and the capacitor. So the voltage drop across the capacitor was initially 0, as we see in the graph, but it increased over time as the capacitor became progressively more charged. So you can see that finally the voltage is almost 1.5 volts. So we have a drop of almost 1.5 volts across the capacitor. So the voltage drop across the resistor has to be getting smaller and smaller. The voltage drop across the resistor is essentially the difference between this line and 1.5 volts. And what that means is that the current through the resistor has to be decreasing over time, and that's why we can see this current line decreasing. So what's the physics going on here? We have a constant 1.5 volts here. Initially, the capacitor is uncharged, 0 voltage drop. So what's the physics here? We have a constant 1.5 volts across from top to bottom. That voltage drop is shared by the resistor and the capacitor. The capacitor is initially uncharged, 0 volts. So that means that we have a large voltage drop across the resistor, a large current, but that current brings charge to the capacitor. The positive charge stacks up on the positive plate of the capacitor, increasing the voltage of the capacitor, decreasing the voltage across the resistance, and also decreasing the current. So the voltage across the capacitor exponentially approaches 1.5 volts. So that's where the exponential comes into our equations for the voltage and the current. Now, what I will do is I will discharge the capacitor. I'll click the switch again, and that will take this whole branch of the circuit out of the circuit. No current can flow over here. So the battery is effectively removed from the circuit. What we'll have then is we'll have a loop consisting only of these two resistors and the capacitor. The positive charge of the capacitor will then flow away through these resistors and into the negative plate of the capacitor. So we will reverse the sense of the current. So we'll get a negative current according to this diagram. So we'll go from having a positive current, which was going this way, to having a negative current. And that will be the result of the capacitor, the voltage across the capacitor, driving a current through these two resistors as it discharges. Let's take a look at that. There you can see the charge draining off of the capacitor. You can see the current going in the opposite sense to what it was before. That current is taking positive charge away from the positive plate and bringing it to the negative plate, in effect discharging the capacitor. The voltage of the capacitor decreases exponentially as the current drains off, and the current also approaches 0 exponentially. It starts off at its greatest value when the capacitor was most charged, and it decreases exponentially. Let's use our equations and to check the time constant of this circuit. The initial voltage across the capacitor, it appears to be about, we'll call it 1.4 volts. So V initial, or delta V initial, is 1.4 volts. As the capacitor discharges, the voltage approaches 0. So if we allowed an infinite amount of time to pass, the voltage would go to 0. So that says that delta V final is equal to 0 volts. The capacitance, C, is equal to 800 microfarads. Let's say mu for micro, so that'd be 800 times 10 to the minus 6 farads. And the equivalent resistance, well, let's see, we have two 10 kilo ohm resistors, so that gives us a total resistance of 20 kilo ohms, and these resistors are in series because since we've opened the switch, any current through the first resistor has to flow through the second resistor. So the equivalent resistance is 20 kilo ohms, so it'd be 20 times 10 to the 3 ohms. And what does that give us for our time constant? Our time constant, tau, is equal to R equivalent times the capacitance. That is equal to 20 times 10 to the third times 800 times 10 to the minus 6. So what does that give us for our time constant? 20 times 10 to the third times 800 times 10 to the minus 6 gives us a time constant of 16 seconds. That is our time constant. So let's use our equation for the voltage. Delta V is equal to delta V final plus delta V initial minus delta V final times e to the minus t over tau. This is the equation that I gave you last time for the voltage across a capacitor. And so that would be delta V is equal to 0 plus 1.4 minus 0 times e to the minus t over 16 seconds. And so let's pick a time. Let's pick 10 seconds. Let's predict what the voltage is at t is equal to 10 seconds. That'd be delta V is equal to 1.4 times e to the minus 10 over 16. So what is 1.4? 1.4 times e to the minus 10 divided by 16. That predicts a voltage of 0.749 volts at t is equal to 10 seconds. Let's take a look at our graph. And here is t is equal to 10 seconds. The voltage, according to the graph, is just shy of this line right here. And this line is 0.75 volts. So we did predict the voltage at t is equal to 10 seconds accurately. We could also predict the time at which the voltage is equal to a certain value. Let's check. We'll take this point right here. According to this graph, the voltage is equal to 1 volt at t is equal to 5 seconds. Let's check that using our time equation. Our time equation was t is equal to tau times the natural log of delta V initial minus delta V final divided by delta V minus delta V final. Tau is 16 seconds times the natural log of delta V initial, 1.4 minus delta V final, which is 0. And we want the voltage to be 1.0 volts minus delta V final, which is 0. So the time at which that should be the case is 16 times the natural log of 1.4 divided by 1. And that predicts that that will be the case at 5.38 seconds. And in fact, if we look here, the graph actually crosses that 1 volt line just after t is equal to 5 seconds. So somewhere around here. So I would say that 5.3 or 5.4 is good. So that demonstrates the principles behind how a capacitor works in a circuit. Let's work some more examples. In the circuit shown, assume that the battery EMF is 20 volts, the resistance is 10 mega ohms, and the capacitance is 2 microfarads. The switch is closed at t is equal to 0, and the question is, at what time t will the voltage across the capacitor be 15 volts? Now there's one more thing that you have to infer from this question, and that is that the voltage across the capacitor is initially zero, that the capacitor is initially uncharged. If the capacitor were not initially uncharged, we would have to be told what its initial voltage is. But the way that this question is written, it expects you to infer that the capacitor is initially uncharged. Okay, let's draw our diagram. The EMF is 20 volts. This is the positive side. The resistor is 1 mega ohm, or 1 times 10 to the 6 ohms. The capacitor is a 2 microfarad, or 2 times 10 to the minus 6 farads. There is a switch here which we close at t is equal to 0, and I will note here that delta V initial for the capacitor is equal to 0 volts. So we are assuming, or we're inferring, that the capacitor is initially uncharged, and it has so its initial voltage is 0 volts. So now we know what delta V initial is. What is delta V final? Well, we're going to close the switch. Once we close the switch, current will flow in this circuit, and ultimately the capacitor will have the same voltage as the battery. So the battery will provide positive charge. Let me say that again. The potential from here to here is 20 volts, because as we go from here to here, we go up 20 volts in voltage. Now, as we go around here, that means that the voltage drop as we go from here to here has to also be 20 volts. So that voltage drop is shared by the battery, by the resistor, and by the capacitor. The capacitor is initially uncharged, so initially there's 0 volt drop across the capacitor. The entire voltage drop is across the resistor. So there's 20 volts across the resistor. That will drive a current across the resistor. That current will turn the corner here. It will encounter the capacitor and the gap. That will bring positive charge to the positive plate and draw negative charge from the negative plate. So the current will flow through this circuit, bringing positive charge to the positive side of the capacitor, putting negative charge on the negative side of the capacitor as it draws off positive charge. So the capacitor will charge, and the voltage across the capacitor will increase. So over time, the voltage across the capacitor increases. And that will decrease the voltage drop across the resistor. As long as the voltage in the capacitor is less than 20 volts, there will be some voltage drop across the resistor and some current. However, as the current continues to flow, eventually the capacitor will charge up to 20 volts, and then we'll have a 20 volt increase across the battery, 0 voltage drop across the resistor, and a 20 volt drop across the capacitor. So there'll be plus 20, 0, minus 20, gives us 0 for the voltage. There'll be no voltage drop across the resistor and no current across the resistor. So the end state, the ultimate end state for the capacitor is delta V final is equal to 20 volts. That is what will happen as time goes to infinity. So with that, all that we have left to do is to calculate our time constant. Tau is equal to R equivalent times the capacitance. We only have one resistor, so R equivalent is just 1 times 10 to the 6. Oh, well, actually, I don't have to write. We're assuming basic metric units, and ohms are the basic metric unit of resistance. So 1 times 10 to the 6 ohms times the capacitance, which would be 2 times 10 to the minus 6 farads. So the time constant is, well, actually, 10 to the 6 times 10 to the minus 6 is 1, so t will be 2 seconds. So the time constant for this circuit is 2 seconds. Then we'll use our voltage equation for the capacitor. Delta V is equal to, oops, actually, I'm sorry. We don't want to know the voltage, we want to know the time. So we'll use our time equation. Time is equal to tau times the natural log of delta V initial minus delta V final over delta V minus delta V final. And that is tau is equal to 2 seconds times the natural log of delta V initial, which is 0, minus delta V final, which is 20, divided by delta V. We're asked to find the time when delta V is equal to 15 volts. So that'd be 15 minus delta V final, which is 20. So we have 2 times the natural log of minus 20 over minus 5. So I'll write that again. T is equal to 2 times the natural log of minus 20. 0 minus 20 is minus 20. 15 minus 20 is minus 5. And minus divided by minus will give us a positive, so that would be 20 over 5. Or you can do negative 20 over negative 5. That's fine as well. Okay, so the time is 2 times the natural log of minus 20 divided by minus 5. And that would be time is equal to 2.77 seconds. So the time at which the voltage is 15 volts is 2.77 seconds, and that is what we were asked to find. Let's work another example. In the circuit shown, the capacitor is initially uncharged. So this time it tells us explicitly that the capacitor is uncharged. At t is equal to 0, switch S is closed, so the switch is initially open and it's closed at t is equal to 0. Find the currents I1 and I2 and the voltages V1 and V2, assuming that V3 is equal to 0, at points 1 and 2 at t is equal to 1.0 milliseconds. Go ahead and draw your diagram and write out what you know and don't know, and start working on this question, please. Okay, let's draw our diagram. We have a 12-volt battery, a 0.050 microfarad, so times 10 to the minus 6 farad capacitor, and we're told explicitly that delta V is equal to delta V initial across the capacitor is equal to 0. We have a switch which is initially open, and we're going to close it at t is equal to 0. Then we have a resistor. And we go back to the battery. And the resistor is 40 kiloohms, or 40 times 10 to the 3 ohms. And this was marked as 0.3. And we're told that V3 is 0. So that's our grounding point. So V is equal to 0. And we're asked to find the voltage at points 1 and 2. So V1, V2 is what we're looking for. And these are at t is equal to 1 millisecond, or 1 times 10 to the minus 3 seconds. At t is equal to 1 times 10 to the minus 3. What are V1, V2, I1, and I2? And this was I1, and this was I2. And one thing we can say right away is that whatever I1 is, I2 is the same. So any current that goes this way has no place to go except down this wire and across the resistor. So those two currents are the same. There's no branching points through which the current can go. So any current here has to be the same as the current here. So I2, we know that whatever I2 is, we know that I2 is equal to I1. So we really only have to find I1. Okay, let's see. We know delta V initial for the capacitor. We were told that it's initially uncharged. What is delta V final? Well, the same logic that we used last time goes into this. The current that flows in this circuit will charge up the capacitor, and it will raise the voltage in the capacitor so that the voltage drop across the resistor will decrease. So initially the voltage drop is 0 across the capacitor and all across the resistor. As the capacitor charges up, the voltage drop here increases and the voltage drop across the resistor decreases, the current decreases, and that will continue until we have plus 12 volts, minus 12 volts, and 0 voltage drop across the resistor and 0 current. So delta V final will be the same as the voltage of the battery. So delta V final is equal to 12 volts. So we know that delta V final will be 12 volts. The last thing that we need is we need the time constant, tau. Tau is equal to R equivalent times the capacitance. Tau is equal to, well, R equivalent, there's only one resistor, a 40, that's 40 kilo ohm resistor, so that would be 40 times 10 to the third times the capacitance of 0.05 times 10 to the minus 6 farads. So the time constant is equal to 40 times 10 to the third times 0.05 times 10 to the minus 6 microfarads, minus 6. And that says that our time constant is 2 times 10 to the minus 3 seconds. 2 times 10 to the minus 3 seconds, or 2 times 10 to the, 2 milliseconds. Okay. So what is delta V across the capacitor at t is equal to 1 times 10 to the minus 3 seconds? Delta V across the capacitor, I'll mark it delta VC just so we remember what we're doing. delta V across the capacitor is equal to delta V final plus delta V initial minus delta V final times e to the minus t over tau. So at t is equal to 1 times 10 to the minus 3 seconds, delta V across the capacitor would be delta V final, which is 12, plus 0 for delta V initial, minus 12, times e to the minus 1 times 10 to the minus 3 seconds, divided by 2 times 10 to the minus 3 seconds. Okay, and so what is delta V across the capacitor in that case? We have 12 minus 12 times e raised to the minus 1 times 10 to the minus 3 divided by 2 times 10 to the minus 3. 12 minus 12 e to the minus 1 times 10 to the minus 3 divided by 2 times 10 to the minus 3, and that gives us 4.72 volts. So delta V across the capacitor at t is equal to 1.3 seconds is equal to 4.72 volts. So we can answer the first question. The first two questions, what are the voltages? And so that would be, if this is 0 volts right here, as we step from 3 to 1 across the battery, we're going up in voltage. So we're going from 0 up 12. So delta V, V, the voltage at point 1, is 12 volts. So the voltage change from here to here is a positive 12. So we're at 0 here, we step up by 12. So the voltage at this point is always going to be 12. Now, as we go across the capacitor, the current that's flowing from the battery is going to bring positive charge to this side and negative charge to this side. So as we go across the capacitor, we're going from positive to negative. We're stepping down in voltage. So V2 is going to be 12 minus the voltage change across the capacitor. So that would be 12 minus 4.72. 12 minus 4.72. And that is equal to 12 minus 4.72. 12 minus 4.72 is equal to 7.28 volts. So the voltage at this point right here is going from 0, 12 minus 4.72 leaves us with 7.28 volts at this point. So that means that delta V across the resistor must be, as we go from 7.28 to 0, delta V across the resistor is 7.28 volts. So we can answer our questions about the current. Delta V across the resistor, as we go from here to here, we're stepping down in voltage. So that would be delta V across the resistor would be 7.28 volts. And that's going to be equal to the current times the resistance. So that would be I2 times 40 times 10 to the 3 ohms or I2, is equal to 7.28 divided by 40 times 10 to the third, or I2, 7.28 divided by 40 times 10 to the third would be 1.82 times 10 to the minus 4 amperes. So the current through the resistor, the current I2, which is the same as I1, is 1.82 times 10 to the minus 4 amperes. 1.82 times 10 to the minus 4 amperes. And that is what we were asked to find: the voltage at point 1, the voltage at point 2, and the currents. And so we've answered all the questions. Let's answer one more question. Capacitors are used in many applications where one needs to supply a short burst of relatively large current. A 100 microfarad capacitor in an electronic flash lamp supplies a burst of current that dissipates 20 joules of energy as light and heat in the lamp. To what potential difference must the capacitor initially be charged, and what is its initial charge? This is really asking about the energy in a capacitor. Remember that the energy in a capacitor, U, is equal to 1/2 CV squared. So the energy in a capacitor is 1/2 of the capacitance times the voltage squared of the capacitor. So what we imagine going on here is that we've initially charged up a capacitor at a certain voltage, given it some energy, then we close a switch and let a current flow through a resistor, and that resistor gets hot and it gets bright, so that's our lamp. And also remember that the voltage difference across a capacitor is equal to the charge on the capacitor divided by the capacitance. You'll need those two equations to answer this question. Let's draw a circuit. Here we have a capacitor and a switch and a resistor. So the capacitor is a 100 microfarad, so 100 times 10 to the minus 6 farads. And it's initially charged up with some positive and some negative. The resistor isn't specified. This is the light bulb, by the way. The flash bulb is the resistor. And then at time t is equal to 0, we close that switch and current will flow from the capacitor to the resistor, and that's what will heat up the resistor and make it glow. So that'll give us our flash of light. What we are told is that the energy that is released in this process, the energy is equal to 20 joules. So a total of 20 joules of energy is delivered from the capacitor to the resistor, and delta V initial is what we're looking for. And also we're looking for the charge, the initial charge on the capacitor. Okay? Well, what we do know is that the energy stored in a capacitor is 1/2 C delta V squared. So that would be the initial energy, so 1/2 C delta V squared. The energy in the capacitor initially is the 20 joules of energy that are delivered to the light bulb. That's equal to 1/2 the capacitance. The capacitance is 100 times 10 to the minus 6 times delta V initial squared. We have everything here except for delta V initial. We'll solve for that. So multiply both sides by 2. 2 times 20 divided by 100 times 10 to the minus 6 is equal to delta V initial squared. Or we'll take the square root of 2 times 20 over 100 times 10 to the minus 6. Let's make sure that that's clear that that's not 2.20. So I'll put parentheses around everything. So 2 times 20 over 100 times 10 to the minus 6, take the square root. That would be delta V initial. And what is that? The square root of 2 times 20 divided by 100 times 10 to the minus 6. Close my parentheses. That would be 632 volts. So we have to charge the capacitor to 632 volts to deliver that much energy to the circuit. The second question was, what is the initial charge? Well, I'll take that back. We know that the voltage across the capacitor, delta V initial, would be equal to the charge on the capacitor divided by the capacitance. So the initial voltage will be equal to the initial charge times the capacitance, or delta V initial we know is 632 volts. That's equal to the initial charge divided by the capacitance of 100 times 10 to the minus 6. And we can solve that for the charge. So 632 times 100 times 10 to the minus 6 is equal to the initial charge. 632 times 100 times 10 to the negative 6. That would be 0.0632 basic metric units of charge, which are coulombs. So 0.0632 coulombs is equal to the initial charge on the capacitor. And those are the two questions we were asked to answer. Finally, we have only one more circuit element to add to our electrical circuits, and that is an alternating voltage source. Up to now, we have been considering only direct current. That means current that flows in only one direction. When an alternating voltage is applied to a circuit, an alternating current, that is, a current that changes in direction with frequency F, results. An alternating voltage source looks like this. Basically, it's a circle with a sine wave inside of it and leads coming out to connect to your circuit. That represents a source of alternating voltage. The voltage of an alternating voltage source, delta V as a function of time, is equal to delta V max, or the peak voltage, the maximum voltage, times the sine of 2 pi times the frequency times the time. So delta V is the maximum. The sine function varies from 0 to 1 to 0 to negative 1 and back to 0. So the largest that the sine function can be is 1, and at that point the voltage will be delta V max. The sine goes to 0 and the voltage will be 0. Then when the sine goes to negative 1, the voltage across the voltage source reverses. So we have a voltage in the opposite direction to which it was before, and that would be a negative voltage. And then it continues to oscillate like this, like a sine wave, forever. F, the frequency, is the number of complete oscillations per second, And frequency is measured in units of hertz, where a hertz is 1 oscillation per second. What kind of source can give us an alternating voltage? There are many kinds, but one, the oldest one, is an electrical generator. An electrical generator converts mechanical energy into electrical energy by rotating a loop of wire through a permanent magnet. Here you see a cutaway of an electric motor. It has a magnet, a permanent magnet with a north pole and a south pole, and a loop of wire rotating through this permanent magnet. As you remember from our discussion of electromotive force, as we rotate a loop of wire through a magnetic field, the magnetic flux through that loop of wire changes. It grows, decreases, grows in the opposite direction, decreases again. So we have a changing magnetic flux through that loop, which induces an electromotive force or a voltage in the loop. Now, as a loop rotates, the voltage will first appear in one direction as the magnetic flux increases, and then in the other direction as the magnetic flux decreases. So the rotating loop of wire gives us an alternating electromotive force, or an electromotive force that changes sinusoidally. So an electrical generator creates an alternating voltage. When we come back next time, we will see what happens when we apply an alternating voltage to our electrical circuits that include resistors, inductors, and capacitors. Until then, think physics.